Well, hello, I'm Zhao. This is our paper regarding topology and adaptability in differentiable diversity-based end-to-end ASR. This is a co-work with Pinzhen Chen and Peter Bell at the Center for Speech Technology Research, the University of Edinburgh. So I will go through the introduction first, and then followed by our method, then experiments, and then we make some conclusions. So first, I would like to let you know why we wrote this paper. We believe that we all like ASR models trained on a training set which can generalize well on other acoustic conditions. We believe that we can change or affect this factor by changing the topology. If that is the case, which part is the main factor, the acoustic modeling power or the internal language model? So here is how we did it. We modified the topology in our differentiable diversity-based end-to-end ASR and see if it will affect the adaptability or the generalizability. We manually created two subsets or two datasets which share the same acoustic conditions but quite different language patterns to investigate the effect of the internal language model. We will talk about that later in the experiment part. Here's basically what we found in our experiments. First, changing the topology does affect adaptability. Second, in terms of adaptability, CTC topology, which is a special case in our framework, is not optimal. Finally, we found that, primarily, the topology mainly affects adaptability by acoustic modeling power. So here, I'm going to briefly introduce the pipeline of our differentiable diversity-based end-to-end ASR framework. So first, this is an emission FST example, which is directly transformed from the neural network outputs, assuming that there are only 5 modeling tokens, which are blank, ank, which is unknown, and A, B, and C. When we are talking about topology, we are actually talking about the topology of the token FST. So here is an example of the token FST with a CTC topology, as you can see in the figure. So here's a lexicon FST example. I think most of you are quite familiar with it, as long as you are familiar with Kaldi. So the training objective is a bit similar to CTC loss function. However, there's a denominator term in our version. So actually, CTC is a special case where the denominator is always 1. However, for most other topologies, the denominator is not always 1 as CTC. So we will have to compute the denominator in most cases. So here's, I'm going to introduce briefly how to compute the numerator and the denominator with differentiable WFST. First, as we can see in the second equation, we compose T, L, and W to get the training graph, where W is just a linear FST transformed from the target sequence. After that, we compose E with the training graph STIN and compute the total score in the log semiring, which is the numerator. To compute the denominator, we cannot take all possible word sequences into account, so we approximate it by composing E and T, and then getting the total score. In this way, we will make sure that all the paths in E can be acceptable in T. As for decoding, we follow a quite standard procedure. We first construct the decoding graph by composing T, L, and G together, where G is a grammar FST usually derived from an n-gram language model, given the outputs of the neural network models, and the decoding graph, we simply apply the V2P decoder to get the final hypothesis. So let's have a look at the basic settings of our experiments. We fine-tune a pre-trained WFTWAC 2.0 model, namely WFTWAC 2 large LV60K, with various topologies. We train our models on WSJ, which has roughly 80-hour transcribed data. We apply phoneme as the modeling units. We evaluated our models on datasets with different acoustic conditions, namely WSJ, Eval 92, LibreSpeech, Test Other, TATLM3, and ARMY. As for the decoder, we apply the decoder decode faster in Kaldi, To investigate different topologies, here are 8 topologies in our paper. The first topology is the traditional CTC topology, which is S1T1 in our naming system. Generally speaking, SXTY means that there are X states for each phone, and the minimum traversal frame is Y, and one more star means one more self-loop added in the topology. So here are the WER results on various evaluation sets. We can see that taking CTC as the baseline, all other topologies outperform CTC, implying that CTC is not an optimal choice when it comes to adaptability or generalizability. We also found that in total S2T2 has the best average performance, which has about 7.2% word error rate reduction. To further investigate either the acoustic modeling power or the internal language model affects the generalizability, so we manually get 2 subsets with similar number of recordings based on Tetlium-3. We assume that these 2 subsets have relatively similar acoustic conditions. However, we apply TF-IDF to make them have different language patterns. Here's the perplexity, and we can see that the language model 0, LM0, has a lower perplexity on depth 0 and plus test 0, but higher on depth 1 plus test 1, and vice versa. So when we then train our models on train 1 and evaluate them on test 1 and test 0 with and without a corresponding language model. Actually, we did not see a clear evidence saying that the internal language model affects the generalizability. On the contrary, we see that even though the model was trained on train 1, but it can still perform even better on test 0. Thus, from these primary results, we cannot say that the internal language model plays a big role in the adaptability of our end-to-end ASR models. Alright, so here are some conclusions. We investigate the influence of the topology. The study confirms that the topology of end-to-end ASR models significantly impacts their adaptability to different acoustic environments. And we also find that adaptability is primarily influenced by the acoustic modeling capabilities of the topology, without reliance on a strong internal language model. And we also found some limitation of CTC topology. So the CTC topology shows limitations, particularly struggling with significant acoustic deviations from the training data. So as for the future research directions, this study recommends investigating diverse modeling units beyond phonemes to potentially enhance model adaptability and performance in future studies. So here's something that I believe to be the weakness of this paper. First, we currently do not have a theory to explain why one topology has a better adaptability than another. Besides, the effect of the internal language model should be further investigated, as our experiments are only limited on small-scale datasets, which may not be sufficient for end-to-end models to learn a strong internal language model, so that we cannot see that in our experiments. Okay, so thanks for watching. If you are interested in our work, please feel free to scan the QR code for the paper and the code.